So the first talk this morning is by Ursula Hamenstadt, and she'll tell us about branch covers of hyperbolic manifolds. Thank you.
Well, thank you very much for the invitation to come here to this beautiful place and to give a talk. It's a great pleasure. So what I'm going to talk about today is very much in some sense hyperbolic geometry. Also, I want to talk about manifolds which are not hyperbolic. So let me start with the following. We start with an n-dimensional compact, say closed hyperbolic manifold. And n will always be bigger or equal than 3. So we assume that there is a totally geodesic embedded submanifold. Embedded here means so then it's really embedded as a submanifold, meaning H is also compact, of dimension n-1, so it's a hyperplane. And we assume in addition that we have a hyperplane in the hyperplane, so sigma is totally geodesic, embedded. And we want that sigma is homologous to 0 in H. So that is stronger, of course, than saying that it's just homologous to 0 in the manifold. And there's a little bit of deficiency of what I'm going to talk about today. Everything should be true in more generality, in higher generality. But at the moment, that's where we stand. So what we can do now is we do the following construction. So homologous to 0 means that H minus sigma can be written as H0 union H1, where these are non-trivial submanifolds. So meaning the sigma cuts H into 2 non-trivial components. So now what we do is we cut M. So I drop now the dimension here, sort of clear what it's supposed to mean. We cut M along H0. And then what we see is we get a manifold which I call M cut. That's a suggestive sort of name for it because we cut, which has a boundary. The boundary consists of 2 copies of H0, so H0 minus union H0 plus, where H0 minus and H0 plus are joined along sigma because we cut only along H0. So how it looks like is, so here we have H0 minus, here we have H0 plus. Here's our manifold in H0 minus and H0 plus. They are joined along sigma. Now, if we are in a situation like this, then we can take D copies of M cut and glue in cyclic order. So glue in cyclic order means, so we take the first copy of M cut. This looks like this. Then we take a second copy of M cut. Let me just draw it in this way. So here we have H0 minus. Here we have H0 plus. And we glue the H0 minus component of the boundary of the second copy of M cut to the H0 plus component of the first copy. Now we can do this so we can keep on going. So we have maybe a third copy. We do the same construction. At the end, we glue the last copy of H0 plus to H0 minus of the first copy. So what we see is then a kind of circle consisting of D copies of M cut. And this defines a branch cover. So this is a branch cover of M branched along sigma. So that's a very nice manifold, which can be explicitly more or less understood. But the question is, what is the manifold as a geometric object? Let me now just point out to you the following. So the theorem, which is due to Perelman, I will explain why it's totally Perlman in a second, which says that if M is equal to 3, then this new manifold, which I should give a name, let me call it X, then X is hyperbolic. So why is that supposed to be true? Let me give you a proof. So what do we know about the X? So the X is glued from these copies of a hyperbolic manifold. But now these H0, this H was totally geodesic. And that means that if we glue these pieces, we glue them with an isometry. So we glue the H0 minus onto H0 plus with an isometry. So this means that X admits a hyperbolic cone metric. So what is a hyperbolic cone metric? It's a beautiful hyperbolic metric, except that is not smooth at the sigma, because at the sigma we glue more than 2 copies of our manifold together. So meaning we glue exactly D copies, and the metric will have a cone singularity along sigma. So sigma will be now my copy of sigma that I see in X. So that makes perfect sense because the sigma sort of survives. So this has a cone singularity along sigma. And the cone angle is 2 pi d. And d is a degree, which is always bigger or equal than 2. So the cone angle here is bigger than 2 pi. So what it looks like is really, I mean, you have the sigma survives in your manifold. The manifold is a smooth manifold. The sigma survives. But in the normal bundle of sigma, which is a disk bundle, now you see a metric which is cut into sectors, where each of these sectors is already cone angle 2 pi, because you glue these different copies here. And then the total cone angle in the normal bundle is just 2 pi times d. Now, if we are in such a geometric situation, then we know that this metric here is what's called a cut -1 metric. So it is, it's not smooth, but it has a curvature bounded from above by -1 in the sense of Alexandrov, whatever that means. But this implies that X is acylindrical, atoroidal. Let me not go into this. It will not be super important for the rest. And by the geometrization theorem of Perlman, this implies that X is hyperbolic. So this means no matter what branch cover you take in this setting here, if the dimension is 3, then all you find back is a hyperbolic manifold. So meaning there's many different ways to construct hyperbolic manifolds, new ones from old ones, not just using ordinary covers, but also branch covers, and you always get back to hyperbolic manifolds. So now you can ask yourself the following question. Let me ask, when did I start? 45, okay, thank you. You can ask yourself the following question: what happens in dimension bigger or equal than 4? And so the theorem I like to talk about today is, this is partially joined with Frieda Eckel. Oops. If n is bigger or equal than 4, then X is not hyperbolic. In fact, X is not locally symmetric, which I will explain in a moment. So here we have a drastic difference between 4-dimensional hyperbolic manifolds and 3-dimensional hyperbolic manifolds, at least concerning this construction. So I would like to give you a little bit of a history of this problem. So remarkably, at least probably more than half of the talks, either the name Gromov or the name Thurston was mentioned. let me here mention Gromov and Thurston. So Gromov and Thurston collaborated, and they wrote a paper where they tried to construct new geometries that are not negatively curved geometries, that are not hyperbolic, and they use this construction. And so Gromov and Thurston so in 1987, they published a paper which, among others, implies so that many of these manifolds that you can construct in this way, if you start with an arithmetic hyperbolic manifold of simplest type, dimension is bigger or equal than 4, then you can construct them in such a way that they admit a Riemannian metric of arbitrarily pinched curvature, but no metric of constant curvature. So in this paper, they prove the following things. You have to prove that the manifolds are not hyperbolic, and they prove that for the fixed M, only finally many x, meaning only finally many branch covers branch along the same sigma, but where the degree of the covering can be arbitrarily large, only finally many can be hyperbolic. And they conjectured that none of them is hyperbolic, and so that is confirmed by our theorem. Now, how did they prove this? The proof is actually given that we heard Roberto Frigiero yesterday talking about, yes? So the X is a cyclic branch cover of a fixed manifold. So that's always denoted by X from now on. So I will not specify the degree because it gets a bit clumsy in the notation. So after Roberto's talk yesterday, the proof is very easy. This proof is very easy. So what you do is, I will just sort of give you an oral account on it. What you do is you look at the branch covers in the following way. First, you triangulate your original manifold in some way, in such a way that this submanifold sigma is contained in the codimension 2 skeleton of your triangulation. You can always do this. It's not very difficult. Now, if you take such a triangulation, then you can lift it to this branch covering, and you see a triangulation of your manifold as well, which has as many top dimensional simplices as you had originally. So what does that mean for the simplicial volume? So Roberto told you yesterday about how to compute simplicial volumes. It means that the simplicial volume of these manifold X here grow linearly with the cover. On the nose, because again, you get an upper bound by the number of simplices that you see. You cannot compute it properly, but you get an upper bound. If you have this upper bound, then you know now the following. So you know that by Mostar rigidity, so you have a deck group acting on X. So the deck group is not a free group acting, but so the generator of the deck group call it theta, has a homotopic representative, meaning there is a generator of the deck group that you see here on the nose by the construction, but there is one that is homotopy equivalent to an isometry if this manifold admits a hyperbolic metric. So if X admits a hyperbolic metric, then theta has an isometric representative. So furthermore, so you can look at the cyclic, you can look at the group generated by this isometric representative. This will be a group of isometries, but now Mostar rigidity is so good that this, if the degree of the covering is D, then this generator here, this diffeomorphism of M, has the order of the cyclic group generated by the theta is exactly D. So most of rigidity is so good that it tells you that the order of the representative here, so theta sharp has order precisely D. So what does it mean is we can now quotient out our M by the group generated by this isometry. We don't know what it does a priori. Sorry, X. So that's here a branch. So this gives you an obifold. Hyperbolic obifold, because you quotient out by an isometry which in general cannot be expected to be fixed point free. But the degree now of the obifold, so now you have a map to this obifold. This has degree precisely D. Now, we get this degree map, and now we look at what it does for the simplicial volume. So if this X is hyperbolic, then simplicial volume equals the volume of the manifold up to universal constant, only depending on the dimension. So if you have here this degree precisely D covering, this means that the simplicial volume of this quotient space here is divided out by D. So we get here orbifolds with uniformly bounded simplicial volume. These are hyperbolic if you're assuming that all of these manifolds here have a hyperbolic metric. It's uniformly bounded simplicial volume. And this means that by a theorem of Wang, there are only finitely many of these can be hyperbolic. So what did Wang prove is, Wang proved that there are only finitely many hyperbolic obifolds of any dimension n bigger or equal than 4, which have uniformly bounded volume, and hence uniformly bounded simplicial volume. And this finishes a proof here that the theorem by Gromov and Thurston, that for fixed M only finitely many can be hyperbolic. Now, in their paper, Gromov and Thurston state something better than what I just say here. So they say that this isometric representative of the deck group has a following property. Let's so Gromov Thurston. Theta has property that the fixed point set of theta of this isometric representative is smoothly homotopic. So meaning it's diffeomorphic and smoothly homotopic to sigma, so to this locus of the branch locus of your covering. So to be completely honest, I don't understand this. And why don't I understand it? So what's the issue here? So we have here your element of the deck group. So let me point this out. So theta generates a finite group of diffeos of my X. So that is very clear. I mean, this is by construction. But now we get the homomorphism, to get a homomorphism from this group to the isometric group of X. So assuming that X has a hyperbolic metric, But now what does it say about the fixed point set? So that is not so clear to me, and I will come back in a moment to this. So the fixed point set of this isometry here that represent this homotopy class does not, a priori does not necessarily be the same as a fixed point set of your original diffeomorphism. And there, so I should say, I'm making a small comment. While I was constructing counterexamples when I came here, I wasn't so sure about the literature, but Bina Chichiku taught me the corresponding reference. So there's a paper by Kapell, Lubotsky, and Weinberger, which says that you take so which says the following: you take, say, n, a closed hyperbolic manifold, and then there are examples. Then there are examples of finite. So they have much more precise statement, which I will not going into. They look more at homeomorphism than not diffeomorphisms, but it works similar in the same way for diffeomorphisms of finite groups of diffeos. Which are not conjugate. So meaning that it is a little bit difficult to contour the fixed point set and say something precisely about how the Mostar rigidity kicks in. So before I get back to you on this, the statement is nevertheless true. I will give you even, so I decided to give you even a little proof. So the proof that you actually do have this property here, that the fixed point set in this case is smoothly homotopic to sigma is true. I will give you a little proof, which is at the end of the day not very hard, but I wanted to include it here to show you that, I mean, this kind of statement, okay, we know Mostar rigidity and we are good, is maybe not so clear at the very beginning. But before I do this, let me give you some more results about these branch covering manifolds, which turns out to be not well studied at all, but maybe interesting. So I have to check here on my references to not screw up the dates. So there is a little bit of work that appeared in the meantime on these branch covering manifolds. So let me give it in chronological order. So Misha Kapovic, showed in 2007 that some, meaning some explicit examples that you get here from explicit arithmetic, starting with an explicit arithmetic hyperbolic manifold, and then take specific branch covers of that sort. Some of these manifolds admit convex projective structures. I conjecture that all of them admit convex projective structures. I mean, all of them that have this, that are constructed in exactly the way I described at the very beginning, where you start with a homologous to zero totally geodesic submanifold in a totally geodesic subhyperplane in a closed hyperbolic manifold of dimension at least 4. Then there is work of Gerald in 17, which says that if the starting manifold can be cubulated, then the branch cover can as well. So meaning now you have cubulated manifolds which are not hyperbolic, but are sort of close to hyperbolic, which may be interesting to study in their own right. So there is work, before I state some more results, let me point out that by the virtue of the power of cut-zero cube complexes, cube-relating nice manifolds like this, we do know that the fundamental group of X is linear, because it injects into an SLN Z for some large n, and it's not the same as the dimension here. But there's some more concrete result, which is due to Montclair, Schlenker, and Toulouse, that has not been published yet, but it was posted on the archive in 23, and it says that for certain, again, I believe that is true, should be true maybe for all of them, for certain, pi1 of X embeds into O of N2. So this is, it's a Lie group which has rank 2. It's, of course, not the isometric group of hyperbolic space. It's the isometric group, I mean, it's related to anti-de Sitter geometry. But this shows that these groups are linear in a very precise way.
And what does cubulated mean here?
Sorry?
So what does cubulated mean here?
You mean that, so you can have the fundamental group. So cubulated here means that the fundamental group of X is a fundamental group of a virtual special cut-zero cube complex. So that means cubulation.
So in particular, if you start from type 1 arithmetic, then all you get is cubulation.
Sorry?
If your M was type 1.
Yeah, sure. Of course, it's of simple type arithmetic, you get it for free. But I mean, the statement, I just give you the most general statement, so it doesn't say anything. So the manifold I start off with may or may not be cubulated. Of course, the examples we know of are basically arithmetic manifolds because we don't know anything else. I mean, you need something with a totally geodesic submanifold of two-dimension 1 that's already hard to get. I mean, you can do Gromov-Piasecki-Shapiro and glue two arithmetic things together, but they're poorly cubulated because you just stick to arithmetic things together, right? So, so most likely, as you point out, I mean, most likely everything can be cubulated in this setting. But again, this is what was shown. All right, thank you. Yeah, so that, and then finally, so there's a last result that I'd like to mention. This is Avramidi, Okun, and Shrev, I don't know how you pronounce his name, in 24. So that was posted on the archive in 24, and they showed that some, so that's even more restricted, so some of these manifolds fulfill the Singer conjecture. And so since this was mentioned before, I just mentioned this result. Singer conjecture says that Altobetti numbers vanish except in the middle dimension. So, so you have here B. Yeah, now I never know where to put the index here. B2 K is equal to 0 except for K is equal to n over 2. But this only works for in very special cases. Okay, so now what I'd like to do is I'd like to give you an outline of the proof of this result. So it has two parts. The first part is essentially, in some sense, fixing here what's not so clear, meaning showing that this here is actually true. So this statement here is true. That's not very hard. This is why I like to present you the proof. The second part is more analytic and is more difficult, and I will just tell you somehow what's going to the proof and where we actually do need in the proof that we don't start with arbitrary branch covers, but we start with branch covers where we look at the branch locus being a hypersurface homologous to 0 in a hypersurface in the manifold. So while I'm cleaning the blackboard, let me also mention that the interest of these manifolds is, among others, because they can be equipped with interesting geometries that are close to hyperbolic. So these manifolds are close to hyperbolic, but they're not hyperbolic as sort of I'm claiming here. And so there may be an interesting class of manifolds to study where actually very little is known. I basically gave you all I know about these manifolds on the list on the left blackboard. So now let's just look at the following proposition. So we assume now that X is now the branch cover, constructed exactly in the way I described of M, and the proposition is, the proposition fixes the statement that is not so clear, without sort of saying a word. So we have theta, the generator of the deck group, so we assume that X is hyperbolic. Then the isometric representative, meaning the unique isometry which is homotopic to theta, has fixed theta star smoothly homotopic to fix theta. Meaning, so in our setting, it will be a submanifold of codimension 2, which is diffeomorphic to the fixed point set of theta here. In particular, if the dimension happens to be at least 5, then Monster rigidity kicks in for the fixed point set. The fixed point set will be now a hyperbolic manifold of dimension of codimension 2, meaning of dimension at least 3. Then Monster rigidity kicks in and says that the fixed point set of the theta star here is precisely isometric to the fixed point set of theta, which you see as a submanifold of your original manifold M. So let me just try to explain to you how this goes. Again, it's not very hard. The first thing to worry is about does theta sharp has fixed points at all. The first claim is theta sharp has fixed points. So why is it supposed to be true? That's a nice exercise in group cohomology. So let us assume that theta sharp does not have fixed points. Now what we know is that then we get a covering. So then theta sharp acts freely, and we get that the quotient space, we can now quotient out by the action of the theta sharp. And this is a manifold, smooth manifold. In particular, it has a homotopy type of a finite CW complex. So however, we do know that the theta has fixed points. Since the theta has fixed points, we can look at the extension of the fundamental group of X by our finite group that is determined by theta. So we get an exact sequence of groups. So there's a group G, which we don't quite understand. And there's a group Z mod dZ, which is the group generated by the theta. And so this is an exact sequence of groups. Then the theta has fixed point, this sequence splits. So meaning this group, actually, if you look at the fixed point, this group acts as an automorphism on pi1 of X rather than as an outer automorphism. Now the sequence splits, meaning that Z mod dz is a subgroup of this group G. On the other hand, this sequence here only depends on the homotopy. So basically only depends on the homotopy type of the zeta, meaning that if you take a zeta, which is homotopic, or say a zeta sharp, which is homotopic to zeta, you get the same sequence here. So meaning the zeta sharp defines the same exact sequence, and this implies that z mod dz is a subgroup of, and now we are back here, we're assuming that the zeta sharp does not have fixed points, so this quotient here is a smooth manifold, and this is a subgroup of pi1 of this manifold. And this is absurd because no finite group can be a subgroup of CW of a finite CW complex. So this is a finite, has a homotopy type of a finite CW complex, and then the fundamental group cannot contain Z mod dz. So that's how you can assume that you have fixed points. This, of course, does not do the job yet. So that was a kind of a relatively easy exercise in group cohomology. And now let me tell you how to soup up from this, using this exercise, how to soup up getting your proposition. You have to use something because, again, as I said here, this paper tells you that you cannot a priori assume that you have just your finite group of diffeomorphism of your manifold, that you know something automatically about the fixed point sets of its elements. So here, since I'm a geometer, geometry naturally kicks in. So, and we will use geometry to this end. So we will use that my map theta, so note, theta is an isometry for the singular or the hyperbolic cone metric. That's by construction. So we have here on this manifold this hyperbolic cone metric that I just obtained by lifting my hyperbolic metric on the original manifold M to my X, and then theta is an isometry. So this means that for X in the fixed point set of theta, we can look at the action on the fundamental group of this theta here. We know that the fixed point set of theta star, so that's now the action of the element theta on the fundamental group of X with base point X. This is equal to pi1 of the component of fixed theta containing X. In general, you might have many different components because your original manifold sigma might have many different components. So that's just an exercise in somehow noting that we are here on a cut -1 space. So meaning if you look at the fixed point set of my element here, which is an isometry, this is a totally geodesic submanifold. Every element in the fundamental group can be represented by a unique geodesic loop, and this automatically already implies that this statement here is true. And now how do we relate this to the fixed point set of my theta sharp? Now you just sort of modify. You know that the theta sharp has fixed points. You modify with a homotopy. That X is also an fixed theta sharp. And so now then you can talk about fix of theta sharp with the same base point. Now you can also modify with a homotopy that your preferred element in the fundamental group of this fixed point set here is also fixed by theta sharp star. So you also choose, again, you do this with a homotopy, choose beta and pi 1. Let me just write it down as fix theta star, and arrange such that beta is contained in fix theta sharp star. You can do this with a homotopy as long as you just have here one element. But now what we know is that the action here, since these maps are homotopic, we know that theta star sharp is equal to alpha theta star, alpha minus 1 for some alpha. And now you see what the beauty here is. So this means now we arranged it in such a way that two things hold. So we know that theta star sharp preserves the conjugacy class of any, say, gamma in fix theta star. Because, I mean, if gamma is fixed by theta star, then we get that theta star sharp of gamma is conjugate to gamma, simply because here we have then alpha is equal to alpha gamma alpha minus 1. And so now we have that the conjugacy class is preserved, and hence theta sharp fixes pointwise the closed geodesic. So any element in any conjugacy class in the fundamental group can be represented by a unique closed geodesic. Freely homotopic to gamma. And from this, it's not hard to see that you see that the entire fixed point set of theta sharp based at this point has to coincide with the fixed point set of theta star, of theta. I mean, the component of the fixed point set of theta that contains this point. So you just sort of go here from the fixed point set by fixing closed geodesics, and you see from the fixing closed geodesics that you can match up the fixed point sets using this geometric picture here. And then you are done with, essentially done with your proposition. Well, that's an outline of the proof of this proposition. So all you need to do is sort of let the geometry work for you and use the fact that every free homotopy class has a unique geodesic representative both for the map theta star as for the map theta sharp as for the map theta. So it works for both maps, and this gives you that these fixed point sets here are smoothly homotopic. So now let me give you an outline of how you do. This was just sort of the easy part of the proof, how you do the rest of the proof, what goes into the rest of the proof, and where we use that we need this totally geodesic submanifold. So the rest of the proof is more of analytic nature. So what do we have now? So we assume that my manifold, so X, again, assume X has a hyperbolic metric, is hyperbolic. Now we know that we have this deck group acting. So the fixed point set of the deck group is a totally geodesic submanifold, which is diffeomorphic to my original manifold, and it's isometric to my original manifold if the dimension is at least 5. So this is diffeomorphic to the original manifold. But we don't know much more. So now what we do is we remember that we have this description of our X being composed of several components of this M-cut. So M-cut, let me remind you, was constructed as follows. You take your original manifold, you cut along this H0. H0 was a component of H minus sigma. And so you have here this description that you see these M cuts, and you see D copies of the M cut in the manifold X. Now you take your sigma, and you construct, well, you not construct, you use some well-known things about minimal surfaces or minimal hypersurface. You construct a minimal hypersurface say, let me call it, say, Q in X with boundary sigma. And so now you choose one of these copies of the H0 that you see upstairs. You see many copies of the H0, but homotopic to a copy of H0 in X. So again, perhaps you have a totally geodesic copy of this H0, you don't know, but at least you have enough information to get embedded. You have to show that this is embedded. You get an embedded minimal hypersurface, which is sitting in this X, and which is homotopic to one of these cut regions, and the boundary is just a sigma. So why does it help us? It helps us in the following way. So you now can cut open your manifold along these minimal submanifolds. So now you notice you take a minimal submanifold, you move it with this isometry, which is just a representative of this deck group, and then you get another minimal submanifold, and you show that these don't intersect. So meaning that you cut X open along the union of theta star Q, and then you see nice manifolds with boundary, but which are homotopy equivalent Z manifolds, which are actually homeomorphic to M cut. And they have, manifolds with boundary homeomorphic to M cut. They have minimal surface, not quite, because there are singularities along the sigma. They have minimal boundary, but they're nice. They're nicely controlled, and they are homeomorphic to M cut. Now, what we do in addition, so we cut M cut along H1, which was a component of H minus sigma, which is not the one we use to construct this M cut. So what this gives us, this is equal to M minus this hypersurface. So you just cut along the entire hypersurface. So you play the same game with M cut. So the result is a hyperbolic manifold, say N, with totally geodesic boundary. So that's nice, but why does it help us? So now we do the same construction that we did, producing these minimal hypersurfaces here, replacing H1 by H0 by H1, which we can, there's no problem. So we get a second hyperbolic manifold with minimal boundary by cutting X. Again, we cut X now, we cut X along these minimal submanifolds, and we see here a second hyperbolic manifold with minimal boundary, and this manifold is homeomorphic to N. So now it's not only homeomorphic, now you have to do something. Why did we all this work here? We have to show in addition, so we have here these two manifolds with boundary, so we have one more information. If we have a hyperbolic manifold with totally geodesic boundary, so this N is the convex core of an infinite volume hyperbolic manifold. So what you just do is you have this, this totally geodesic boundary, and so you just sort of add a flaring end, and you get automatically a convex, infinite volume n hat, whose convex core is equal to n. And now we do the same thing with our other mysterious manifold. There's also a hyperbolic manifold, which is obtained in the same way by just somehow extending this minimal surface boundary to something that is a complete hyperbolic manifold of infinite volume, so we get a second copy. You have to be a little bit careful here, but we get a second copy, second manifold. Say n bar, so this has infinite volume. But now what do I know about the fundamental group? The fundamental group of pi 1 n bar is equal to the fundamental group of pi 1 of n hat. And furthermore, this alone is not good enough, but furthermore by construction, so n bar and n hat are quasi-isometric. And here you use the explicit construction. Again, you use these minimal surfaces and the way you produce these manifolds to show that these guys here are quasi-isometric. So how do we use this to our goal? Here have a theorem. So we have a theorem which is due to Kerckhoff and Storm. And I will explain to you what that theorem means, which says that if n is compact manifold, hyperbolic manifold, so that was published in 2012, with totally geodesic boundary, then there is no of dimension, dimension bigger or equal than 4, that's absolutely crucial. Sorry for this. Then there's no infinitesimal deformation of n. What does that mean? So it means that unlike in dimension 3, if you have a manifold, a compact hyperbolic manifold with totally geodesic boundary, you can deform it within the hyperbolic manifolds. You can just keeping the fundamental group fixed, but in the character variety, there is a deformation space. This deformation space can be explicitly described. But what Kerckhoff and Sturm showed that this is not possible in dimension bigger or equal than 4. So more concretely, you can describe what the deformation, the tangent space, or the virtual tangent space of deformation space is supposed to be. So this virtual tangent space of the deformation space is the first cohomology with coefficients in the flat bundle, which comes from the representation itself. So let me just write this down. So the statement is the following. The more precise statement is the following. So you have H1 of n with coefficient in the flat bundle. Now it gets a little bit complicated. I will write it down in more precisely in a second. So it's in, maybe I write it down this way, in SO n, 1. So that's supposed to be Gothic letters, hard to produce. So that's a Lie algebra of SO n, 1. This is equal to 0. It's trivial. And what is this cohomology? That's something that can be described in terms of the Ram cohomology as follows. So you have, so N defines a representation of pi 1n into O, the isometric group of hyperbolic n space, which is, let me write it down this way, O plus n1 is various ways of writing it down. And so this representation here, so let me call it rho, this defines a flat bundle via the adjoint representation. So what you do is, you just do the following. You define a flat bundle with fiber the Lie algebra of this group. The Lie algebra is SON, 1. And this flat bundle is given by, you take your element, so to get the flat bundle, you need a homomorphism from pi 1 of n into the linear group of SO, linear group of this vector space. So, and you get it using the adjoint representation. So rho of gamma is equal to the adjoint. That is kind of bad. So the representation, I should write it down a different way. So say phi psi of gamma is the adjoint representation of rho of gamma. And the adjoint representation acting on the Lie algebra of your group. Now this defines this, so this defines a homomorphism of pi 1 of n into the linear group, or the group of linear automorphisms of your Lie algebra, and hence you get a flat bundle. So get a flat bundle. And now what is this H1? This H1 is just the de Rham cohomology with values in the flat bundle. That's one way to see it. So what it just means is locally, the bundle has a flat trivialization. So meaning it has a basis which is parallel for the corresponding flat connection. Let me just write it down as maybe E1, EK for the case, the dimension of the Lie algebra. And now what you just do is you look at one forms on your manifold which are closed with respect to this representation with values in the Lie algebra. So you write down the one form in terms of the value of the one form in terms of the spaces. Now if you take a basis element, then you just get an ordinary one form, meaning so you write down your one form with values in this Lie algebra in the form some alpha I EI. You get here the alpha i's are ordinary one forms. For ordinary one forms, it makes sense to be closed, and it also makes sense to be exact. And so what you do is you look at all closed one forms modulo the exact forms in this fashion here. And being closed or exact does not depend on the flat trivialization here. Everything is local. And if you run through this program, then you see that the abstract tangent space of your deformation space is just this cohomology here. And what Kerckhoff and Sturm showed that this thing here is equal to 0. And now let me, for the last sentence of my talk, let me just tell you how we use this. So we assume again here that we have this quasi-isometry. We run the Mostar rigidity program, the traditional way to do it, using quasi-conformal mappings to prove that the existence of this different metric, which is quasi-isometric to my original metric here, implies that you have a non-trivial class in this group here. But Kerckhoff and Sturm showed that this cohomology group here is trivial, so you get a contradiction to hyperbolicity. And this is the end of the proof. And here you can see where we use totally geodesic. So totally geodesic, I mean, the way we construct these branch covers, again, we use that we start off with a codimension 1 totally geodesic submanifold. This goes in the proof only at this step here, because the Kerckhoff and Sturm is only valid in the setting, and we need to produce this manifold here, this compact hyperbolic manifold with totally geodesic boundary to run the Kerckhoff and Sturm program. And that's the end of my talk. Thank you very much for your attention.